Hello, my friends. Finally got my ass in gear, and I'm gonna do this lecture here with no video. You don't need to see me. Just imagine a scraggly looking dude. I'm sure you can pretty much picture that. You've lived with me the whole semester. So I wanted to get this lecture in before class, and as requested in person, I want you to watch this before class Monday, and I want you to work along with this lecture. So pretend you're in class, follow along, don't just skip through the slides. You're going to miss stuff. I'm going to say some stuff that you need to hear to get that bonus for watching this. This actually, it's not a bonus, it's just a freaking assignment. So, the assignment is watch this. And to get credit for the assignment, you have to do the steps that I will describe in this lecture coming up. I'll be very explicit about what you need to do. It's actually pretty simple, but it'll be easy to miss if you're not paying attention. So, you with me? Cool. Let's start with a quick review, quick overview. We've talked about some types of series, some infinite series. Our first kind we talked about was a geometric series. And you see that form right there in blue. And notice how I wrote it out. It looks a little weird because I put that plus underneath, but that's, plus dot dot dot, like I was encouraging everyone to do on Friday in person. And like I will encourage you to do for the rest of the semester, all 3 days of it. So, what we can do there is we can look at a series, and you should always write out the terms of the series so you understand the rhythm. I beg you, I had to beg people over and over again in person, please do this. Hey, let's start writing stuff. People start writing stuff. No, start writing the series first. That's the step one. So I'm doing that. You do that. The geometric series is the one kind of series besides telescoping that we actually can completely control and own and sum in the case that the common ratio R is less than 1 in magnitude. So that means, again, that R is between -1 and 1. Otherwise, that series will diverge. And then we talked about P series, and I introduced this in more um, detail last Friday. And a P series has a fixed exponent on the denominator. And what changes is the base in the denominator. So it's kind of the flip of a geometric series. In a geometric series, what moves from term to term is the exponent. In a P series, what moves from term to term is the base. In other words, the thing you're raising to a fixed power. So power fixed in a P series. That can be a little tricky to recognize. I'm not going to try to be tricky. We don't have a lot of days left, so we're really just going to get to it and knock this shit out. All right, and then telescoping series. In a telescoping series, for us, there's more generality that could be here, but you have a sum of a fraction. You can assume there's a one on top. There might be another number on top. You could just pull that number out front and get it to look like this. So you've got this 1 over a polynomial that we can factor, or maybe it's given to us factored. And then we use partial fractions on that. We start writing out the partial sums, maybe write out S1, fully write it out, S2, fully write it out. And then from there, try to generalize what is the nth partial sum. And what you'll find in a telescoping series is that lots of things cancel. And so what we're trying to figure out is what is canceling here? What am I left with as the net sum after I do all that stuff? And you'll generally end up with, something like, let me get a pen here. You'll end up with something like S sub n equals, 1 minus some critter here that'll be a thing that goes to zero as n goes to infinity. And then you'll get this sum. Now, that number out front's not always going to be 1, but that number out front will be the sum of the series. That will be the limit in the end. So that's a quick review of what we've talked about series-wise. We've also talked about one test for divergence, and that was aptly named the divergence test. What you're going to see today is another test, another couple of tests for convergence or divergence. But our first test that tells us immediately if a series diverges is if we look at the terms, so you strip off the sum, you're looking at the things being added up, and you want to see, do these things go to zero? When I have this sum that looks like this stuff has to die out. If you're adding infinitely many things, again, if I'm stacking infinitely many blocks, the blocks need to get smaller and smaller. That should be just the thickness, not the width there. But the blocks have to get smaller and smaller if I hope for this thing to not keep rising and have some ceiling on it. So that's what the divergence test tells us. Now let's take a look here. My note app has been acting up, so I got to be a little careful. I don't want to delete more than I need. So let's look at this series right here. Again, step one, write out the series. No offense, you're not good enough yet to look at these things and see what's going on. I'm barely good enough at that. I still have to write this out. Help your brain by writing things. I'm going to do this in green. So what does this series look like? Okay, things to watch out for. This doesn't start at n equals 0 or n equals 1. This starts at n equals 3. So my first term is 3 plus 1 over 2 times 3 plus 1. And then my next term is going to be 4 plus 1. So n goes up by 1. And then I've got 2 times 4 plus 1 plus blah, blah, blah. Keeps on going. Probably want to write out first 3 terms. I just ran out of space there. So let's see, what does this look like? We've got 4 over 7 plus 5 over 9. And at this point, now I catch the rhythm. The bottom is progressing along the odd numbers from 7, 9, then up to 11, 13. And the top numbers are just going up by 1 each term. So the next one's going to be 6 elevenths. Next one's going to be 7 thirteenths, and so on and so on. Now, by looking at that, I have no idea if the terms are going to 0 or not. You might think you do, but that it can be very misleading. That first number, 4 sevenths, that's a little more than a half. 7 thirteenths, that's a little more than a half. Where are these things going? I don't know. So to know that, to actually get an answer, I have to do the limit. So let me get me eraser out here. This thing's been acting like it's never seen me before for some reason. It's like making me go through all sorts of initial steps. Let's get rid of this. We saw it. You can come back and look at that if you need. And you can pause this video as you see fit. But the thing that I'm looking at here is the general term expression. Now I'm going to ask you, pause for a minute. What does that do as n goes to infinity? Answer it before you hear me. Pause. Pause the video. I'm gonna let you do the pauses. I'll say pause when I want you to, but since you have control over this, why sit here longer than needed? Pause. Okay, I come back. And this limit is 1/2, and you can see that in a variety of ways. L'Hopital's rule, you can just look at it and see that you have a first degree polynomial in n on the top and in the bottom. So the limit is the ratio of the leading coefficients, 1/2. And that is not 0. So that means what this series looks like way out at the tail end. So we've got, our first term was 4/7, and then we had a bunch of stuff, but way out here, way, 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 n is a billion. These things are almost a half. And I'm just adding a half plus a half plus a half over and over again. And that's just going to keep building. That cannot settle down to a finite value. So this, by the divergence test, since a sub n converges to 1/2, which is not zero, the series diverges. That's diverges. That's super crammed and shitty. But I want you to also think in terms of sentences when you decide on something in regards to series. That's the hard part here. I was talking to someone in class just right after class the other day. This stuff is new. This is why people think Calc 2 is hard. So just, tread carefully, make sure you understand what's happening. Let's move on to our next test. We're not going to really use this test a lot, but I want you to be aware of it. And in particular, it's because it tells us what we need to know about p-series in terms of convergence, which I actually forgot to freaking say. When we come back, when we had a p-series, that series will converge if the exponent is bigger than 1. If it is not bigger than 1, the series will diverge. And the way you would come up with that result is by using this integral test to convince yourself of that. So what does the integral test say? If I have a decreasing function that is always positive, eventually, this means eventually. So at some point, the function, so I've got this function here. Here's f of n. Here's n. This function might be negative at the start, and it might even be increasing. But as long as at some point, and I'm going to say that point is k sub 0, as long as at some point, eventually it's decreasing forever and positive forever, this result can be applied. So that function, that f of n, that's just an expression for the nth term. So here, back in this example, this is the f sub n I'm talking about. It's just a way to notate that. And we just call that a sub n. But we're thinking of it as a function when we think about the integral test. See, look at that. Now there's stuff on that page, but this mofo is not showing it. And I don't know why. I don't know if I paid for this. There we go. Because any amount is too much, clearly. So if the nth term, if I treat it like a function and I integrate from the place where it starts being positive and decreasing up to infinity, if this integral converges, remember what that means? It's finite, and we can actually get a finite value out of it. There's not some kind of weirdness happening where it's just like a sine curve and we're trying to add areas that, well, that wouldn't even work because that's negative. So just thinking in terms of the area under that function that represents the nth term, if that area there is finite, then the sum is finite. So finite means converge. So if this integral is finite, aka converges, then this sum converges. Check out this if and only if. That's what that stands for, if and only if. And what that means is that it's a stronger type of conditional. Remember how we talked about if P then Q? This is if P then Q and if Q then P. So it's two conditionals put together. It's very strong, and it says these two things on the side, this and this, act the same. When one is true, this here. I didn't put the word converges in here, so this would have, because there's not actually a statement. So if the series converges, then the integral that represents that series or can represent that series converges. If the series diverges, then the integral diverges. This is useful because we can now turn a series into an integral and decide just by using calculus, does this thing converge? Let me give you an example. Let's get a nice color out here. And of course, it's slow on the colors. So a nice purple. So does this series, let's see, I'm going to give you this one, 1 over n cubed. And we're going to say n equals 1 to infinity. So we actually already know this converges. It's a p series with p equals 3. Do you see that? So I know it converges, but let me prove that it converges using the integral test. So this 1 over n cubed is decreasing starting right at 1. It's I've got 1 over 1 cubed, 1 over 2 cubed, 1 over 3 cubed. Just thinking about the terms, not adding them. I'm just thinking about the list of things that I'm adding. That list of things is decreasing. It's certainly always positive because n is a number between 1 and infinity, and that's always positive. When you cube something positive, it is also positive. So this satisfies the fact that 1 over n cubed is positive and 1 over n cubed is decreasing. I'm going to use that little arrow, down arrow, to say decreasing when n is bigger than or equal to 1. So now I can convert this, and in the statement up here, this thing, I replaced n with x. You don't have to, but it's just that, being a mathematician, I think of x as a continuous variable, n is a discrete variable. So here I'm going to put the limits of the sum. So n equals 1 to infinity is where we're decreasing in positive. And then I just replace the n with x cubed. Now I compute that improper integral. And so to do that, I would, of course, go to a limit, replace that upper infinity with b. That's limit as b goes to infinity, x to the negative third dx. I'm going to start at I'm going to actually insert a page here. See, now this used to be really simple. And I would click plus and it would know, of course, oh, I see, it's just stupidly slow. Weird. Maybe I need to restart the iPad. I don't know. But let's look at this. So we had 1 to b, limit as b goes to infinity, x to the negative third dx. So that is limit as b goes to infinity. Then I do the antiderivative, and that's negative 1/2 x to the negative second from 1 to b. That is limit as b goes to infinity, negative 1/2 b to the negative second minus, so it becomes a plus 1/2, 1 to the negative second. And we know that 1 to any power is 1, so this is just a half. And this b to the negative second is easier to think about when we just move it to b squared underneath the fraction bar. And as b goes to infinity, we can see, I almost said it's easy to see. I told you on Friday how I hate it when anyone says that about anything, especially math, and especially when I say it. So luckily I pulled out of that nosedive. And what I see is that this limit is a half. That is finite. Since it is finite, this integral converges. And by the integral test, thus, this series converges as well. So we can use this type of reasoning to show that since this integral, and we talked about this a long time ago, 1 over x to the p dx Since that converges when P is bigger than 1, we have our result for series. See how I'm writing less than infinity? That's just a way of saying converges. So that's the integral test. And I honestly doubt I'm going to ask you to do much with that. But you're listening because you know there's some stuff coming up. Well, let's see. Maybe it's on this page because we're going to move on to the next test. Now, I've avoided the proof of the integral test. And I think I'll just put a little video up of that, of somebody else doing it, because I kind of want to get to the stuff here. Oh, okay. Well, no, your thing that I'm going to ask you to do is not here yet. Must be coming up. This is the test I really want you to focus on. It's the ratio test. This test is going to help us knock out a lot of stuff. So let's go through it. We've got a series, sum of a sub n. Here's how you perform the ratio test. So I give you some series, and I ask you, does the series converge or diverge? So what you do is step one, you compute this limit L, which is the limit as n goes to infinity of the ratio of subsequent terms. The ratio of subsequent terms. So it's the limit of the n plus first term divided by the nth term. And a better way to think of this, and you're going to want to write it like this all the time. Well, you're going to want to write it correctly because when I look at that, shit is wrong. This should say n plus 1 right here. So that's a n plus 1 in that term. And I guess I got to find the freaking green and everything. Plus 1 there. So notice how I turned the division into a multiplication. I took the reciprocal of the nth term times the n plus first term. And I'll explain how to do this in multiple examples on the next page. But let's look at how we use this. We compute that limit. That's going to be some number. It's going to be a non-negative number because we're slapping absolute values on there. So if we have minus signs or anything like that, we're going to strip those off and we're going to compute that limit. So that's going to be a non-negative beast. So if that number, L, is less than 1, the series converges. If that number L is bigger than 1, the series diverges. And if L is equal to 1, this test doesn't tell us anything. It's inconclusive. So I'll show you examples of all these things right on the next page. But what I'm going to recommend to you is pause this here and write that down. On your sheet, where you're keeping all your series stuff organized, you should have one sheet. If you don't, start making it now. It should have on it this stuff. It should actually also have what is the sum of that infinite series? It should have the divergence test on it. And yeah, don't put integral test on it, but put this test on it. So you're going to have part of that sheet that's kind of got the archetype series in it, little box around that. And then you're going to have a list of tests for convergence and divergence. And so far, all you've got is divergence test and ratio test. And of course, if it's a geometric series, you've got the test. The test is right there. Is the common ratio less than 1? Notice how that's kind of like this. It looks very similar. And we'll get to that in a minute, why that might be the case. Oh, oh wait, where the fuck was word 1? Did word 1 disappear? You know what? This goddamn program, pardon my language there. See, this says word 2 here. Uh, I gave you a word 1 earlier and it freaking disappeared. So I guess I'm gonna have to give it to you here. So here's what you need to do to show me you've watched this video. You're going to send me an email by Sunday evening. If I get this Monday morning, it doesn't count. No, I tell you what, actually, just send, no, okay. Send me this before class. I will not remind you of this. You cannot do this when you show up for class. You will not get credit. This is an assignment. And the assignment is, so before Monday's class, and you better be there. Like you've got 3 days. We're going to be doing, every day is going to be insanely busy. Before Monday, send an email to me, trenery@regis.edu. And in the subject line, it's going to say golden bean. That's your subject line. That's all it has to say, and that's exactly what it should say, no more, no less for credit. In the body of the email, they're not going to put anything except a less than sign followed by a number 3, hit return or space or whatever. That's it. If you don't know what that might do, well, you'll find out. It'll convert into an emoji. So that's it. Send me that before Monday. This is an assignment. It's not a bonus. I want to see this in the grade book as a perfect. And so this is Boolean. What was that word I just said? Boolean. That means you either do it or you don't do it. So 0 credit or full credit. Unless you do something weird and you like hose this up somehow. So you got it? Send me an email. Golden bean. Subject. Inside the email, less than 3, return or space. Hit send. That's it. Before class on Monday, I'm not going to remind you again, and I will not accept this late. All right. Sounds good. Next, stupidly slow page. Oh, we're going to do some examples. That's what we're going to do. So let's take this example here, sum of k over 2 to the k, and check it out. Who knows, I might add more to that assignment. If I did that, that would be tricky and probably smarter than I've actually set this up to be, but you might want to hang around. So I'm going to give you an example here. The example is this. This series, does it converge or diverge? Converge or diverge? We are going to use the ratio test on it. And I'm kind of thinking that just given that we have 3 classes left, I will always tell you what test to use. Okay, does that sound good? I will do that for you. So one of the hard parts about this can be that I give you a series and you just have to figure out what test to use. That can be a little brutal. I'm not going to do that. So first step, what do? You write out the series. What does this look like? So k equals 1, k equals 2, k equals 3, k equals 4, plus dot, dot, dot. Put those in. This isn't a finite sum. This is an infinite sum. Oh, okay, wow, looking at that, no idea what's going on. So I'm going to use the ratio test. So I identify the nth term. And you could use a sub k. That's cool too. I'm just changing it to be consistent and to practice using different indices. So that's an plus 1. That's an. So now, look, this thing here, this sub n, you can think of that as a box. So that everywhere an n occurs, that box is present. So it's really like that. It's a function. It's a function of n. where we emphasize that in the integral test, but now it's really, we need to understand that now, that this a sub n is really an f of n. It's a function of n. And why do I say that? So that it makes it easy for me to now write a sub n plus 1. So I'm going to put n plus 1 in each of these boxes. And that means the n plus first term is this. N plus 1 over 2 to the n plus 1. Now I'm going to compute limit as n goes to infinity of a n plus 1 times 1 over a sub n. And I think that's what I wrote back. Well, who would know? Because this piece of shit program, look at that. I just wrote that. Like, seriously, iPad, bro, this is just writing. I'm not trying to render some 3D image here. Come on. Oh, God. I'm afraid to even go back. I'm gonna go back. Okay. One more. So what I'm writing is this expression. Just I'm putting the a sub n plus 1 first. Let's go slow so that our iPad friend doesn't get overwhelmed. Okay. So now I'm going to compute that L. I'm going to just start at the top here so we can see this all on the same page. Yeah, I'll just erase where I wrote out the series. So L equals the limit as n goes to infinity. Absolute value. The absolute value here doesn't play much of a role because everything is already positive, but I'm just writing it down for the time being. That will change. What we've got here is that. So the top n plus 1. So right now I'm putting the a sub n in, a sub n plus 1 in. So I replace k with n plus 1 and here and there. So I've got that. Times the reciprocal of a sub n. Now remember, a sub n is this. And so the reciprocal of that is just flip it. So it's 2 to the n over n. And this is 1 over n. And now things get simple, or things need to be simplified. I don't know if they're simple or not. But we need to cancel what can cancel here. So take a minute, find that limit. I'm going to take a real-time pause here because I have to step to the restroom. Cancel what can cancel there. Here's a thing. Don't cancel the n plus 1 in the n. They don't cancel. But what does cancel? Okay. My wife, I'm driving out there today. It's actually looking not too bad, but I just worry about her. So if you heard any of that, that's what was going on. All right, well, hopefully you've got that limit by now and you've done the simplification. This is limit as n goes to infinity of, as I said, the n plus 1 and the n do not cancel. But the 2n over the 2n plus 1 cancels to 1/2. So I've got 1/2, and then this stuff here that's moving. And what is that limit? Well, I hope by now in this class you can tell that that limit is a 1. So this whole limit is 1/2. That means that this ratio, this L, is less than 1. And so this series converges. Got that? So I would maybe summarize this now. I would show this work, and then I would say by the limit test, uh, sorry, Jesus, by the ratio test, this series converges. Cool. Let's do another one. I'd like you to do this one. I'm going to give you one here. So I have sum n cubed plus 2 over n squared plus 1. N equals 2 to infinity. Doesn't really matter what that starting index was. I just made that up. I had written 1 in my notes, and I thought I'd change it because it don't matter. Make it 30. Make it 427 if you want. Doesn't matter what it is. We're going to do the ratio test. So here's my request of you. Use the ratio test to decide, does this converge or does this diverge? So find L, which is the limit. Then goes to infinity of, let me get you started here, the n plus first term. So a sub n plus 1. That means I replace every n. So that's the a sub n plus 1, and then times 1 over a sub n. Again, just flip that sucker. So that's n squared plus 1 over n cubed plus 2. Now this could be tricky, and I'm gonna say to you, don't multiply out n plus 1 cubed. Don't multiply all this stuff out. Try to be a little more clever about it. Because look, what do we got on top? We're going to have some polynomial in n on top. We're going to have some polynomial in n in the bottom. When we have a limit of a ratio of polynomials, all we need to know is what is the number in front of the highest power of n on top and the highest power of n on the bottom. So this is going to equal limit n goes to infinity. What's the highest power of n that's going to end up on top? So like, what's the highest power of n here? It's going to be n cubed. What's the highest power of n here? It's going to be n squared. So what is, when you multiply this, and it's literally 1 n cubed and 1 n squared, and you need to think about why that is if that is not something you see immediately. And maybe multiplying those out is the way to see that. But you can think it through otherwise. And that's good for you to do. So I've got this 1 n cubed thing, blah, 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 times an n squared plus 1. What's the highest power of n, and what's the number in front of it? And so what you're going to have here is something n to some power over something else, n to some power, and then plus a bunch of crap we don't care about. Pause, think, come back. So the number it's going to be here is a 1. This is going to be a 1. Why do I feel like nobody paused? Just felt that in the ether. And this is 1 n to the fifth. This is 1 n to the fifth. So I got a 1 n to the fifth on top plus lesser stuff. On the bottom, I got 1 n to the fifth plus lesser stuff. That limit, since I have equal degrees on the polynomials, the fifth degree and a fifth degree, that limit is the ratio of leading coefficients. It's 1. What did the ratio test say? I'm sure we're going to have to wait. Oh no, amazingly. If that limit is 1, this test is inconclusive. So we do not know. We might need another test that I'm not going to talk about today. So like right now, our answer is this is equal, since the limit is 1, the test is inconclusive. Hmm. Is there another test that might help us here? What do the terms themselves? And right now we're just talking about the ratio test. I wanted to show you an inconclusive thing, but that actually could be resolved with another test. Let's go back to this series. So what does it look like? It's this. Started at 2. 2 is on top. What is the nth term test? So I'd say, excuse me, the divergence test. That's just another name for divergence test. But we're not using that this semester. But by the divergence test, what? Now, little words of wisdom here. The divergence test can never tell you something converges. It can only tell you something diverges. So right now, I'm leading you toward this suspicion that this thing diverges. Prove using the divergence test that this series is divergent. Pause, look up the divergence test, use it. In fact, I'm going to pause because I have to go get more tea. I'll be right back. This is a real time pause right here. Apply the divergence test. I'll be right back. All right, I'm back. So let's go through this together. Kind of told you needed to happen here and what the result will be, but it's the doing it and understanding what needs to happen. Again, the divergence test says that if the general term, so I've got this series, if the terms do not die out, then the sum diverges. So here, a sub n is that critter. There are multiple ways to see that this actually goes to infinity. But let's first just think about what happens when I take limit as n goes to infinity. What is the top doing? Blowing up. What's the bottom doing? Blowing up. So that's a L'Hopitalable kind of situation. And I think I'll just proceed by L'Hopital's. You know what? No. I'm going to divide the top. Yeah. So you could divide the top and the bottom by n squared. And let's just do it both ways. Okay. So this is the limit as n goes to infinity. Top divided by n squared is n plus 2 over n squared. Bottom divided by n squared is 1 plus 1 over n squared. As n goes to infinity, this goes to 0. So the bottom is going to 1. But the top, let's see, that's going to 0. This is going to infinity. So I get an infinity over 1. That limit is infinite. You could also apply L'Hopital's rule twice to get essentially this. You would get, if you applied L'Hopital's rule twice, you would have on top 6n, and then on the bottom, you would have 2. And you can see that that's just 3n, and that also goes to infinity. So divergence test gets us the answer the ratio test couldn't get us. Let's do one more. So this one is different. And I'm going to put it up here, and I'm going to ask you to just maybe take a stab at it. But it's got a little thing in it that we saw once long ago, but haven't seen it since then. So that is 10 to the kth power over k factorial. I want to point out something here. When you're starting to do this, I'm going to set you up. And writing that as a multiplication problem, because then things just, it's easier for canceling. It'll be good for your brain. Limit as n goes to infinity. So this thing here, a sub n plus 1 is 10 to the n plus 1 over n plus 1 quantity factorial times the reciprocal, which is n factorial over 10 to the n. Lots and lots of things are going to cancel. I'm going to pause. You should pause this. Pause it. Pause it and think. Okay, thanks. Or not. I'm coming back. So what is this equal to? This is limit as n goes to infinity of, now on top, the 10n plus 1 and 10n, you've got one more 10 on top than you had on the bottom. So I got a 10 left on top. Think about these factorials. Let's just do a little scratch work here. I'm going to make an observation here that really makes it all fall apart nicely. N plus 1 factorial is just n factorial times n plus 1. You got to hit n factorial before you get to n plus 1 factorial. Remember, that is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1, assuming n is bigger than 3. So it's the product of all the numbers 1 up to n multiplied together. And when I make this observation, I can see that those two cancel, and that's just 1 over n plus 1. So here I get n plus 1 in the bottom. And that, my friends, is equal to 0 when I take the limit. That just goes straight to 0. So since that L is equal to 0, and that is less than 1, the series converges by the ratio test. All right, that's enough. You probably can bear this. Might even take you a couple sessions to get through. I honestly have no idea how long I've been talking. I hope to hell it recorded. I can tell you that. So I'm going to put up a few web work problems, and you will see those if you watch this lecture all the way to the end. So that's the other secret part. And what are you going to do? You're going to send me an email with the title Golden Bean. And inside the email, nothing else but less than 3 space or enter. Send me that. And then start the web work. All this must be done before class Monday. You don't have to get far, but I have to see that you've attempted anything in that web work. And that's the closure of this assignment. So there's two things to do. The email, try the web work. Man, if you can knock out the web work, I'm gonna make it super small, break, right? But it's not quite the break we are looking forward to yet. So I hope you all have a beautiful break. I hope you do get some rest. I hope you take care of yourselves, you sleep in late, whatever you need to do, get out and hike. I hope that whatever experiences you have with your family and friends are pleasant, non-political, and loving toward each other. So I wish you light and radiance and all the best wishes in the world. And I will see you on Monday when you have all these things done, these simple things to do. All right, be well, my friends. I'm going to get this posted. I'm going to get that web work put up. It's going to be tiny. It's just going to be all ratio test. So every problem on that web work is going to be the ratio test. And it's just, like I said, it'll be real small. I just want you to start getting some practice. All right, be well. Much love. See you soon. Bye.